Hello everyone. In this video, I wanted to go over some things that are sort of useful, especially if you want to continue a little more on in quantum mechanics and that are more conceptual in nature, but that we haven't necessarily talked about a whole lot directly in lecture. In particular, I wanted to go a little more into some things that are usable as operators. This idea that we've started out with momentum, where we see that kind of acts as an operator on the wave function. And also talk a little bit about superposition of states. We haven't really talked very much about the different things that you can actually do with the wave function. So to start out with, we've seen that when you're calculating position, for example, you can get the average position just by sticking an x into this integral, um, where you do this integral and hey, you get the average value of position. And that's very simple. But when you get into momentum, it gets a little bit more complicated because we can think of momentum, whoops, as being an operator on the wave function, where what it does is we actually have this h bar over I derivative with respect to x dx. So we can actually write over here, we're going to write x operator. Position operator is just x. It's just really simple. But the momentum operator, we write that as actually h of r over I d by dx. And we've done a few homework problems where you can kind of generalize this a little bit. You can think of almost everything or really everything in the Schrodinger equation as an operator. For example, you have this first term that's the minus h bar squared over 2m d squared by dx squared. Where does that really come from? Well, we can think of that really as kinetic energy. It's really the same thing as the expectation, not the expectation value, but it's really the same thing as p op squared over 2m. If this were classical physics, p squared over 2m would just be, for kinetic energy, would be 1/2 mv squared. That would be the kinetic energy. What we mean here by p op squared is that we act with the operator twice. So it's not really that we're squaring that term exactly in the usual sense. It means that we're taking the derivative twice. So let me just write out what that does to a wave function. That means that I act on a wave function, then I can pull out the constants at least. So I've got an h bar squared and then the I squared at the bottom. That turns into a -1. So that gets me the minus h bar squared over 2m. That matches up with the Schrodinger equation term. And then I get two derivatives, but I just want to be clear about how I write that. It means I take the derivative, I use the first momentum operator, and then I act again with the second momentum operator. And really, we call that a second derivative, and we write that as d squared. We even write it as if it's sort of the square there, but really it's a second derivative. We've also seen that you can treat the potential term as an operator. Usually that just has some x's in it, so it's usually pretty simple. The potential energy usually just depends on position. But we can, in fact, think of the entire left-hand side of the Schrodinger equation as an operator called the energy operator, where we say that the energy operator is sort of defined as the p squared over 2m kinetic energy operator, basically, plus whatever the potential is doing as an operator. This is pretty simple with what we've been doing most of the time so far, because most of the time we've been looking at wave functions where you act with the wave function, you act with the energy operator on the wave function, and it gives you the energy. So that has just a number, so that's pretty boring. But the reason I wanted to bring it up now is that I wanted to also talk a little bit about superposition of the different states and what that means. So we've said that let's take the simplest example, our infinite square well potential, where we had our wave functions were really just like standing waves, and so on. And we labeled them n equals 1, n equals 2, n equals 3, and we had that the wave function in general was some amplitude, which I'm not going to bother with, sine n pi x over L as our wave function. And then we said basically each of those, just from the equation, each of those has a specific energy. And not all energies are allowed. You only get specific values of energy, and those are the solutions to the wave function. What I want to emphasize now, though, that we haven't looked at too much yet, is that, for example, if psi1, that's a wave function with the ground state energy, it satisfies the Schrodinger equation. Psi2 is another solution that satisfies the Schrodinger equation. But the Schrodinger equation, it's a differential equation, and it's a linear differential equation in the sense that if these two individually satisfy the Schrodinger equation, then if I take some linear combination of them, that also solves the Schrodinger equation. This is also, this wave function, I could just call that a new wave function. I could call that, I don't know, combo wave function. I'll say C for combo. This combined wave function solves the Schrodinger equation. So it's a solution. That means, at least based on that, we can't physically rule it out. Mathematically, it works. And in fact, you can get into situations like this. Now, the interesting thing is that this is a sum of states. It's a superposition of states with two different energies. So that means if you do a measurement or something that actually requires a specific value of the energy, then you're going to have to get one or the other. And that's where these things come in, and we can compute probabilities. So let's, for example, just already, before we even look at that, what happens, we want to make sure our combo state is also normalized, that the probability of the thing overall being anywhere is 1. So what we want is, the integral we want the integral of our combo wave function times its complex conjugate over all possible positions to be 1. We want that. But if we just plug in what this combo state is, then we get A star psi1 star, A psi1 integral dx equal to 1. We get another term, B star psi2 B psi dx infinity to infinity. Getting a little sloppy over there. But, and then we get cross terms. We can have A star psi1 star B psi2 dx plus the other cross term. I'm just going to write other cross term. I'm not going to write it out because guess what? This is actually a general property of wave functions, but if you look in this case, look at our wave functions. They're sines, sine n pi x over L. If I take two sines with different wavelength, multiply them together and integrate over some fraction or half integer fraction of wavelengths, they cancel. Like this one times this one, integrate that out, cancel. And n equals 1 times n equals 3, integrate it out, it cancels. These cross terms are just 0. That's why I didn't even bother writing out the second one. And then if we look at the two terms remaining, this just separates out into, sort of isolate that off there, basically the magnitude of A squared, and then I can pull those, those are just numbers, those are just coefficient of how much my combo state is in psi1. It might be complex, but I can pull that out of the integral. So I have a star times a, and I'll just write that as magnitude of a squared. What's left in the integral is just the integral of psi 1 star times psi 1. But if that state's normalized, if that wave function is normalized, which it should be, which we've done that, then that is just equal to 1. So that integral just goes to 1, and all I get left out here is the absolute value of squared of a, and then this term similarly gives me the absolute value squared of b. So what I get left with is this requirement that if I want my combo state to be normalized, then my coefficients a and b have to satisfy that constraint. So that's what normalization means for the combo state. But still, okay, so a and b are sort of like they're coefficients. They can be complex numbers. They do satisfy this constraint, so they seem to be somewhat like probabilities, but they're not quite like probabilities. Maybe the square is like a probability. But let's do one more thing, and we can actually see how that works. Let me save that at the bottom. Let's look at, for example, let's look at the energy operator. Like I said, normally we've been looking at that and it's just simple, like the energy is just a constant. But now we have a superposition of two states with different energies. So what happens if we look at, let me write back down our combo state. Our combo state is a times psi 1 plus b times psi 2. What is the energy operator? What is the sort of expectation value for energy? Let me actually write it out this way. I'll write expectation value of energy, the integral of psi star c energy operator times my combo wave function, integrate that, and there we go. So what do? We can use the left-hand side of the Schrodinger equation, but we actually can break this combo state up into its components, and then we know what the energy operator does. It just returns a number. So that's actually really nice. Then we get, again, we're going to get, we write this out, we get 4 possible terms, but 2 of them are cross terms. They go away because we do the integral of psi 1 times psi 2. It just does nothing. So I can write this as a star e. Remember, the energy operator when it acts on psi 1, so for example, E op psi 1 just equals E1 psi 1, the energy of the first ground state. Energy operator acting on psi 2 is just E2 psi 2, the energy of the second state, of the n equals 2 state. So when I put for my combo state, when I put this all together, I get 2 terms. I get a star, and the energy operator operating on this gives E1. I have an A in there. I haven't done the integral yet, so I have psi 1 star and psi. But when I integrate that, that's going to turn into 1. And then my other term is basically B star E2. I've kind of moved terms around, but psi 2 star psi 2. And there's some dx's and other tedious stuff. Anyway, point is, my expectation value for energy has turned into something very similar. I get the magnitude squared of A times E1 plus the magnitude squared of B times E2. So we can very much kind of interpret these A and B coefficients as being related to probability. So if I have my combo state where I put it in a superposition, then A squared, A magnitude squared, is basically the probability that I'm going to find it in that first state, whereas B squared is the probability that I'm going to find it in the second state. So this kind of terminology gets used a lot when doing quantum mechanics, and in fact superpositions of states are very important because there's nothing that says that you can't do it. And in fact, you can prepare a wave function in as to be a superposition of states, and that turns out to be actually very useful.